Welcome to the Deep Dive. Today, we are strapping into the electric revolution, but probably not the one you see on the public roads. We are diving deep into the hidden battleground of modern Formula Student motorsport, the digital domain.
That's absolutely right. For decades, Formula Student Racing, which is, the ultimate proving ground for the next generation of top automotive engineers, was all about the mechanicals.
Right, it was horsepower, aero, how good's your chassis?
Exactly. It was all about those mechanical engineering challenges. But the technology landscape has, it's fundamentally shifted.
And shifted hard.
Mhm.
The modern vehicle is really defined by its software, making it a software-defined vehicle, or an SDV. And the FS grid, which is always pushing the limits of electric powertrains, is leading that charge. The competitive edge is no longer just about, optimizing physical grip. It's about the resilience, the integrity, and the absolute speed of the electronic and electrical architecture. The biggest threat a team faces today isn't a suspension failure.
Not anymore.
It's a zero-day digital exploit that takes control of the torque vectoring.
Precisely. And that's why this deep dive is so critical. We are unpacking a massive, highly detailed engineering requirement specification, an SOR, the kind of blueprint a top global automotive engineering strategy consultant would create.
So this isn't just theory.
Oh no, this is a custom-tailored strategic roadmap. Our mission here is to transform cybersecurity for a new university team, turning it from a compliance footnote into the core competitive advantage you need to build a world-class electric racer.
Okay, let's unpack that strategic intent immediately using that high-level consulting lens. We are moving beyond just building a fast car. We are building a safe and secure car. But what makes security so necessary right now?
It's regulatory, yes, but it's more importantly, it's architectural. Cybersecurity, codified by standards like ISO C 21434 and regulations like UNISR 155, is now an absolutely essential pillar. It sits right alongside, and it has to be co-engineered with functional safety, which is ISO 26262. You can't just design the safety systems and then try to bolt on security later. It doesn't work. They have to merge.
And the philosophy behind it all.
The central design philosophy underpinning this entire SOR is absolutely clear. Zero trust.
Zero trust. That's a term you usually hear for massive corporate networks or military defense systems. Applying that to a tiny, high-performance student race car seems almost hyperbolic.
It sounds aggressive, I know.
Yeah.
But it's the only responsible approach in an environment where speed and safety are this critical. It means we assume that every single interface, the Wi-Fi telemetry unit, the charger connection in the paddock, even the wires leading to the pedal sensors, is potentially compromised.
So you assume you've already been hacked, essentially.
You have to. This forces the system to be inherently self-defending. It must rigorously verify the legitimacy of every single message and every component, even those communicating internally. And if that verification fails, even for a moment, the VCU has to immediately go to a defined fail-safe state. No second chances.
That's a huge commitment. It forces engineering discipline right from the very start. So if this SRR is meant to be a strategic blueprint for success, what are the, say, 4 key performance indicators it aims to achieve? What's the measurable definition of success here?
Right, so we define success using a MAZE approach, mutually exclusive, collectively exhaustive, which is just standard for strategic planning. The goals are fourfold and they're all integrated.
Okay.
First, compliance. 100% adherence to the latest global rules from FSG 2025, FSAE 2025, and FSC. Compliance is just the price of entry. Failure here means you're disqualified. That's mission failure.
Simple as that. Second, safety. Preventing catastrophic system loss of control. This is specifically focused on neutralizing digital attacks that could cause unintended torque delivery, which leads to a crash or trigger thermal runaway in the high-voltage battery. S3 critical safety events have to be impossible through digital means.
Third,
data sovereignty. This is a huge, rising, critical area for international competition, specifically for Formula Student China, where regulations demand strict localization of important data, like vehicle trajectory. The architecture has to be globally compliant, not just in your home country.
and finally, the big one for any race team.
Performance. This is the critical trade-off. We have to maintain communications latency below a punishing threshold of 500 microseconds.
Half a millisecond.
Half a millisecond. Implementing heavy authentication and encryption cannot introduce delays that compromise the VCU's high-frequency torque vectoring loop. If security slows the car down, it has failed its primary competitive purpose. That 500 microsecond requirement alone just highlights the tension, doesn't it? Security has to be completely invisible to the driver. That sets the stage perfectly. Let's move into the regulatory framework, because in Formula Student, the rule book is, well, it's the Constitution. You mentioned this represents a strategic shift from mechanical to digital warfare. For a new team, how does adopting standards like UNES R155 actually translate into a competitive edge, rather than just being a massive headache?
It's the difference between doing security as a checkbox versus doing security as a competitive design philosophy. Compliance, when you look at it through a strategic lens, isn't bureaucracy. It's providing a rigorous framework for building robustness and quality assurance. By adopting the principles of UNES R155 and ISO 21434, the team is forced to implement a simplified cybersecurity management system, or a CSMS.
A CSMS, that sounds like something General Motors would use, not a university team. What are the bare bones of that system for our purposes?
For a world-class student team, the CSMS is really about process clarity and accountability. It means clearly defining roles like you must appoint a dedicated cybersecurity officer from day one.
Okay.
It means defining secure development processes, like using specific coding standards and creating a formalized incident response plan. Now, here's the competitive punchline. The massive benefit comes during the static design evaluation, the engineering design event.
Ah, the design presentation where they just grill the engineers on the choices.
Exactly, and teams that treat security as an afterthought fail here. A team that presents documented, systematic evidence of a CSMS showing their threat analysis and risk assessment, their TERA, their secure design choices based on ISO 21434, and their defined roles, they gain a huge competitive edge.
Right.
They demonstrate a professional engineering rigor that far exceeds teams that just say, oh, we used a firewall. The judges reward maturity in process, and the CSMS is the framework for that maturity.
That makes perfect sense. It's a shortcut to demonstrating engineering excellence. Let's get into the technical specific rules, starting with the highest bar. Formula Student Germany, FSG 2025. You highlighted the mandatory official data logger as a strategic threat.
The data logger is the ultimate Trojan horse. FSG rules mandate this device for monitoring the high voltage bus voltage under 600 V and total power output under 80 kilowatts. It's required for official scoring and safety monitoring.
But logically, it just reads data. Why is this required piece of monitoring equipment such a risk?
Because the data logger, by its very nature, is a physical link connecting the high-trust powertrain systems, the PT CAN, to the low-trust external world, usually through an easy-access Ethernet port or Wi-Fi for quick data download in the pits.
Oh, I see.
An attacker who compromises the logger's generic operating system, maybe through a known Linux vulnerability, has essentially gained a pivot point directly onto the powertrain CAN.
And the ultimate threat there is what?
Two things. One, tampering with energy consumption data to manipulate scoring, which is bad. Two, and far worse, is using that compromised logger to inject malicious control commands, masquerading as the VCU, onto the PT CAN. This could lead to unintended torque, the ghost driver attack we'll talk about later.
So how do we mitigate that highly specific, very real threat?
The requirement, REQ-FSG001, is to mandate either a unidirectional gateway or extremely strict firewall filtering between the data logger and the PT CAN. The architecture has to enforce a fundamental principle. Data can only flow out to the logger. Control commands cannot flow in from it.
So it's a one-way street digitally.
It has to be. The VCU must treat the data it sends to the recorder as untrusted output. If the physical link is bidirectional, the gateway has to logically enforce that unidirectional flow, maintaining the integrity of the powertrain loop at all costs.
Turning mandatory scoring equipment into a critical security component that really shows a level of complexity. Moving on, FSG also requires integration of the remote emergency system, or RES. This is typically a high-quality physical radio system.
Correct. These RES systems are often SESIL-3 rated. They're very robust hardware. They directly control the physical shutdown circuit, the SDC. The problem is that while the physical relay is robust, the RES receiver also broadcasts its status, the go or stop signal over the CAN bus to every other controller, including the VCU.
Wait, why is the digital signal necessary if the hardware relay is handling the physical shutdown?
Well, the VCU needs to know the system status digitally to manage its control strategies. For logging, diagnostics, maybe initiating a controlled deceleration sequence. But this digital broadcast opens up the opportunity for a replay attack.
Okay, talk me through that replay attack in this context. Why can't the system just ignore the digital signal if the physical wire is robust?
An attacker, having monitored the CAN traffic during a safe run, records a perfectly valid GO signal packet broadcast by the RES receiver. Later, if the vehicle is stopped remotely, say due to an incident, and the SDC is physically open, the attacker replays that previously recorded Go packet. If the VCU relies solely on that CAN message, it receives a forged Go signal. It might then try to close the contactors, or more dangerously, assume the high-voltage system is operational and attempt to output torque. That leads to logical confusion, diagnostic errors, and potentially catastrophic inverter damage.
That's classic cyber-physical failure. The digital layer is overriding the physical reality. How does the SOR guarantee resilience against this specific attack?
RDQ FSG 002 enforces dual-channel verification. This is textbook safety security co-engineering. The VCU software must simultaneously check two independent channels.
Two sources of truth.
Exactly. First, the physical reality. The hardware relay status of the SDC via a dedicated low-voltage GPIO pin. And second, the digital status, the status word received over the CAN bus from the RES receiver. If these two channels are inconsistent for more than 100 milliseconds, we allow a small window for settling time. The system must immediately enter a latching safe state.
So it prevents the digital layer from ever overriding the physical safety logic.
Never. That's a hard requirement.
That's a powerful example of using redundancy to counter digital deceit. Now, let's pivot slightly to the U.S. counterpart, Formula SAE FSAE 2025 rules, because their philosophy on the shutdown circuit seems fundamentally different. They focus almost entirely on hardware.
It is, and it's a critical philosophical divergence that dictates our security focus. FSAE rules mandate that the critical shutdown circuit must rely on non-programmable logic. We're talking relays, hardware interlocks, discrete components, maybe simple logic gates. The rationale behind this, REQ FSAE 001, is an inherent concern about the reliability and security of software itself when you're dealing with absolute safety boundaries.
So if the software is inherently distrusted for that absolute safety layer, what does that mean for our cybersecurity efforts? We can't rely on the VCU to be the ultimate protector.
It simplifies, but also sharpens, the security focus. Our cybersecurity efforts have to focus on protecting the control strategy, not replacing the hardwired safety. If we detect a sophisticated network attack, say repeated failed message authentication on the PT CAN, the response isn't simply a soft measure like setting the motor torque to 0 in software. An attacker could circumvent that.
You want a physical response.
Absolutely. The required action upon detecting a network attack should be to actively open the physical safety circuit. For example, the VCU detects the attack and immediately cuts the power to the main SDC control relay, physically disconnecting the high-voltage supply.
Got it.
This is the crucial distinction. You're linking the detection of a digital breach directly to the enforcement of the hardware safety boundary. The digital intrusion forces a return to the trusted physical safety state.
That brings us to the international wrinkle, Formula Student China, or FSC, which forces the team to consider global data compliance. This sounds pretty far removed from the actual track competition.
It is perhaps the most strategic requirement, linking engineering to global regulatory affairs. China's Regulation on Management of Automobile Data Security defines specific vehicle data, like high-resolution trajectory logs and driver monitoring images, as important data. If a team wants to be world-class and compete in Shanghai, they have to solve this.
And what are the consequences of non-compliance here?
Severe. Legal and competitive consequences up to being banned from the country with their car. REQ FSC 001, which targets data sovereignty, is non-negotiable. If the team uses any cloud telemetry platforms, they have to ensure the architecture supports multi-region deployment. Data streams for FSC competition must be immediately switchable to compliant localized servers within China, preventing any unauthorized cross-border transfer of this important data.
So the data architecture has to be modular and geo-aware. And the second requirement deals with potential cameras or imaging systems.
Yes, REQ FSC 002. Concerning visual privacy and security. If the car uses onboard cameras, say for advanced driver assistance or future autonomous research, the system must implement geofencing technology based on confirmed GPS location.
Okay.
When the vehicle detects it's operating within sensitive, predefined areas like specific track regions or potentially near restricted zones, it must automatically cease image collection or apply real-time blurring to visual feeds. This minimizes the risk of capturing sensitive environmental data.
It's clear that building a world-class Formula Student electric car in 2025 means being just as savvy about international law and data compliance as you are about carbon fiber and battery cells.
Absolutely. And this just confirms that the effort put into building that simplified CSMS process, including the Terra, isn't just about avoiding penalties. It's the foundation that allows the team to operate globally and demonstrate that engineering maturity during the critical design presentation.
With the regulatory context firmly established, let's look at the actual electronic architecture that supports this zero-trust model. You said that flat CAN networks, where every component is just on one shared bus, are insufficient. Why is a flat network an unacceptable security risk in modern high-performance EE design?
The analogy is simple. A flat network is like having one key for your entire house, your car, and your bank vault. If one lock is picked, everything is exposed.
Right.
In an FS car, if a single vulnerable component, like a simple Wi-Fi module in the telemetry domain, is compromised, the attacker has immediate, unfiltered access to every safety-critical message on the bus, including the raw torque commands. To implement zero trust, you have to establish clear security boundaries.
And that boundary creation leads to the required three-layer zonal control architecture. Let's detail how these zones define the level of trust and the flow of communication.
Okay, so first, Zone 1. HV Powertrain Domain Highest Trust. This is the inner circle, the control loop. It houses the vehicle control unit, the VCU, the inverter, the battery management system master, and the motor controllers. Communication here happens only on a dedicated, high-speed, physically isolated bus, the PTCN.
And the policy.
The policy here is absolute, strict physical isolation, and every single node must be mutually authenticated using cryptographic methods.
Okay, that's zone 2.
Zone 2, Chassis and Safety Domain, High Trust. This domain handles crucial but secondary components. The dashboard, steering encoders, and critical sensors like puddle position and the brake system plausibility device, or BSPD. We need to trust these inputs for control, but we must protect the PPCN from them.
How do you do that?
The policy is that communication from Zone 2 to Zone 1 is tightly controlled via a secure gateway. For instance, only validated pedal sensor data is permitted, and limited display data is allowed to flow out to the dashboard.
And the final zone is the Wild West.
Exactly. Zone 3, Connectivity and Telemetry Domain, Zero Low Trust. This is the hostile zone. It includes the telemetry unit, GPS, the data logger, and any external connectivity interfaces. The security policy here is that this zone is considered inherently untrusted. All data originating from here must be meticulously examined. This requires Deep Packet Inspection, or DPI.
Checking the content of the data packet, not just the header.
Right, and you need extremely strict rate limiting to prevent an attacker from flooding the internal network in a denial-of-service attack.
The moment you introduce zones, you need the bedrock of trust to communicate between them. This means security has to be built on the chip itself.
Precisely. You cannot secure bad hardware with perfect software. RVQ-HW-001 mandates that the VCU and the BMS master units must use microcontrollers MCUs equipped with built-in hardware security modules, HSM, or secure hardware extensions, SHE. This is the root of trust.
For our listeners, what exactly is an HSM? Is it just a protected memory area?
It's far more than that. Think of the HSM as a physically isolated, independent, cryptographic coprocessor living on the chip. It's like a bank vault with its own tiny security guard. It has its own operating system, and it can't be accessed by the main application core.
And what's its job?
Its primary jobs are securely storing cryptographic keys, executing complex cryptographic functions very quickly, like AES or hashing and managing the secure boot process, all in an environment that's physically hardened against tampering.
What are the industry standard examples for an FS-level vehicle?
For a world-class system, the recommendation leans heavily toward the Infineon AU-RRS TC3XX series. It's standard in high-safety automotive applications because it has a completely independent HSM core and offers light and fast hardware acceleration for AES-128. For subsystems where cost is a constraint, like secondary BMS nodes or dashboards, the ST Microelectronics STM32H7 is a good option because it still offers hardware acceleration and secure boot features.
So the main takeaway is you have to offload crypto from the main CPU.
It has to be offloaded to a physically separate HSM.
And why is separating the keys so crucial? It brings us to REQ-HW002, protecting secrets.
Because if the main application core, which handles all the driving logic, is compromised through a software bug, say a buffer overflow attack executed remotely via telemetry, the attacker now has access to the main memory, the flash, or the RAM. If the cryptographic keys for CAN authentication or encryption are stored in plain text there, the attacker instantly gains the ability to perfectly forge any message and completely subvert the system.
So the HSM is the only safe place for those keys.
Absolutely. Cryptographic keys must be stored exclusively in the HSM's secure storage area or one-time programmable OTP memory. The SR strictly forbids plaintext storage in standard flash or RAM. This protects the ultimate secret, the trust anchor, even if the rest of the application is running untrusted code. If the key leaks, the entire security framework collapses.
We focused on digital threats, but let's return to the competitive reality. Physical access. The paddock is an open environment. What about physical security against a rival team?
This is a practical competitive threat. REQ HW003, Physical Paddock Security, addresses the assumption that a rival team might get 5 minutes alone with your car. Their goal isn't to hack it remotely, it's to use a laptop and a debugger to read your proprietary control algorithm firmware or tamper with calibration parameters.
So how do we block that physical access?
We mandate that in competition configuration, all MCU JTAG SWD, the debug and programming interfaces, must activate readout protection, RDP Level 2, or the equivalent locking mechanism offered by the specific chip vendor.
Wait, I've heard about RDP. RDP Level 1 simply blocks external read attempts. Doesn't Level 2 go a step further and physically destroy the data if an unauthorized read is attempted?
That's correct, and that's the strategic deterrent. RDP Level 2 ensures that the debug port cannot be used to read or dump the firmware binary from the flash memory. Crucially, if an attacker attempts to override this protection, the chip often performs a mass erase of the internal flash.
So it bricks itself to protect the secret sauce.
It defends the intellectual property, not just by blocking access, but by guaranteeing destruction if the access attempt is malicious. This protects the team's investment in sophisticated algorithms like torque control loops or regenerative braking strategies from competitive theft while the car is unsupervised.
Securing the hardware is one half of the battle. The other half is, well, understanding the enemy. The entire defense strategy rests on the structured methodology of the Threat Analysis and Risk Assessment, or TARA.
The TARA methodology, which is mandated by ISO 21434, is where we merge security with functional safety. We are performing a deep dive not just into potential attacks, but into the potential damage they cause, linking it back to our S3 critical safety events from the Hazard Analysis and Risk Assessment, the HAR.
So it's about strategic allocation of resources.
Exactly. You don't spend $1 million protecting a blinking LED, you spend it protecting the torque request signal.
Let's quickly review those high-priority assets, the components whose integrity is S3 critical.
All right, first, A01 torque request signal integrity. An attacker causes unintended full torque acceleration, that's catastrophic, S3 critical.
Okay.
Then A02 BMS, voltage temperature data integrity. An attacker spoofs data, leading to overcharge or ignored thermal events culminating in thermal runaway, also S3 critical.
The battery fire.
The battery fire. Then A03 RES, stop signal availability. An attacker blocks the remote shutdown signal, immediate loss of safety control, S3 critical. And finally, A05 VCU firmware authenticity. An attacker injects tampered firmware to alter safety limits or disable monitors. This gives them complete persistent control, S3 critical.
Those are the nightmares. Let's dissect the attack paths that lead to these failures, starting with AP01, the CAN bus injection, or as you called it, the ghost driver attack. How does a simple broadcast injection lead to an S3 event?
The vulnerability lies in the design legacy of the controller area network. Standard CAN is highly efficient and fast, but it was designed decades ago for reliability, not security. AP01 assumes an attacker gains access via a compromised diagnostics port, a vulnerable telemetry module in Zone 3, or even a physical splice. They then inject a forged torque command, for example, the VCU's specific torque ID 0x0C0.
And the problem is the inverter, which is waiting for that torque command, receives a packet with ID 0x0x0C0. It has no idea who sent it.
Exactly. Standard CAN lacks any native sender validation. It's purely a broadcast system. The inverter cannot distinguish between the legitimate VCU in Zone 1 and a malicious packet injected from a compromised component in Zone 3. The attack mechanism is simple. Recording and replaying a full-throttle packet at an inconvenient moment, like during a corner or a braking zone, causing the vehicle to accelerate unexpectedly.
That immediately proves the inadequacy of the flat network model. And the countermeasure, Secosine or Leia, has to solve both sender validation and timing, which we'll get into.
Precisely. If we don't implement that cryptographic validation, the ghost driver attack is trivial.
Let's move to attack path AP02, the thermal bomb, targeting the most valuable and most volatile component, the high-voltage battery.
APO2 targets the battery during the relatively unprotected charging window. Charging often happens using external, often less trusted hardware via a separate CAN bus connection in the paddock. The attacker performs a man-in-the-middle attack, intercepting communication between the external charger and the internal BMS.
So the attacker sits invisibly between the two systems. What do?
They intercept the charger's periodic voltage query to the BMS. The attacker then spoofs the BMS's reply, forcing it to deceptively state, "I am not yet fully charged," even if the battery is at its maximum state of charge and maximum voltage. This deception induces the charger to continue forcing current into a full battery,
Which leads to overcharge, cell damage, potential venting, and eventually thermal runaway and S3 critical event.
The weakness exploited is the trust placed solely in the digital CAN bus communication during a critical energy transfer process. The technical countermeasures have to be layered. First, mandatory application layer handshake verification. A specific cryptographically authenticated sequence must be exchanged before the charging relay is closed. And second, crucially, the BMS must have a physical hardware over voltage protection, or OVP, cutoff that is independent of the CAN bus.
So if the digital layer's breached, the physical layer trips the circuit.
It has to, based on raw voltage readings, saving the battery pack.
Layering physical and digital defenses is a clear pattern here. Finally, ATO3, the blackout attack, focuses on Zone 3, the wireless layer, which is often attacked by rival teams.
This is a classic denial of service or performance sabotage attack. The simplest version is a radio frequency jammer used by a competitor to block the team's Wi-Fi or LoRa connections, causing a data blackout just before a critical endurance run.
Which is inconvenient but doesn't stop the car.
Right. The more advanced and dangerous attack is hijacking the link to send malicious parameter adjustment commands wirelessly.
Like secretly changing the VCU's maximum torque map or regenerative braking limits?
Exactly. Stealthily reducing the car's performance margin. The required technical countermeasures are intense. To mitigate jamming, we mandate robust link detection and, ideally, implementation of frequency hopping spread spectrum if the radio hardware allows it, making it harder to target. To counter hijacking, we demand strong end-to-end encryption with rolling code authentication and, as we'll get to, a secondary two-factor authentication for any parameter adjustment command.
It's clear that in a competitive environment, you just cannot trust any wireless link. That zero trust concept is definitely earning its keep. Now we move to the technical specifications, the solutions derived directly from that Torah. We start with the core engineering challenge, securing the CAN bus while maintaining performance. This trade-off between security and speed is, it's brutal.
It is the defining constraint of powertrain design. The control loop requires sub-10 millisecond latency, ideally running at 500 kilobps or even faster with CAN FD. Standard heavy encryption is a non-starter. The overhead just kills the real-time performance.
So we need specialized lightweight security. REQ COM 001 mandates lightweight authentication, LEA. How does this protocol solve the sender validation problem without introducing unacceptable latency?
The key is the compromise on the cryptographic signature size. We use AES 128 CMAC to generate a full message authentication code, or MA. The MC is the digital proof of integrity and authenticity. However, a full MC is too long for a single standard CAN frame, which only has an 8-byte payload.
Right.
If we tried to send a full MC, we'd have to fragment the message across multiple CAN frames, which instantly adds tens of milliseconds of delay.
And milliseconds matter immensely in this context. So we trade size for speed.
Precisely. The genius of LEA is the truncated MC. We only append a small portion of the full MAC, specifically 16 to 24 bits, to the CAN frame's data field. This is just small enough to squeeze into the available payload space, maintaining the single-frame transmission and thus preserving real-time performance.
Okay, but the idea of a truncated MC screams compromise. We are sacrificing cryptographic strength for pure speed. If we only use 16 bits, isn't that dramatically easier to brute force than a full 128-bit MBC?
That is an absolute excellent question that goes right to the heart of real-time embedded security analysis. And yes, 16 bits is only 65,536 possibilities. In a non-real-time setting, an attacker could guess that MC in seconds. But here's the critical distinction. The attacker doesn't just need to guess the MAC.
Okay.
They need to guess it simultaneously with the next required monotonic counter, the freshness value, all within a punishingly short 10-millisecond transmission window, and without knowing the master cryptographic key that is secured deep inside the HSM.
Ah, so the rolling counter adds the essential time dimension to the security.
Exactly. The monotonic counter is an anti-replay mechanism. The VCU maintains a counter that only ever increases. This value is included in the MAXE calculation. The receiving ECU, the inverter, verifies that the counter value is greater than the last received value and that the MAXE calculation is correct. So if an attacker replays an old legitimate packet, the counter will be out of date, the MAXE verification fails, and the message is instantly discarded.
So you're trading ultimate theoretical security for practical, high-speed security in a very constrained environment.
That's the game.
Even with truncated MSAs, this authentication process adds data overhead to the PT CAN. What is the performance constraint in REQ Common 002 that manages this overhead?
This is a hard performance constraint. The authenticated CAN bus load, even with these lightweight methods, must not exceed 70% utilization at peak. Exceeding 7% risks introducing message jitter and latency, which will violate the real-time performance requirements of the control loop.
And if the design exceeds this,
the strategic advice is clear. Either employ grouping strategies, sending a full MIC only every N frames for less critical high-frequency data, or, ideally, upgrade the hardware foundation immediately to CAN NFD to gain that critical larger payload capacity.
moving to the brain of the vehicle, the VCU. If we can't trust the code running on the VCU, nothing else matters. How do we ensure the software starts securely?
We enforce a robust startup process known as the chain of trust, which is mandated by REQ VCU 001. This is the cryptographic guarantee that the code the VCU is executing has not been tampered with since it was signed by the engineering team.
Walk us through the links of that chain of trust, from power on to application launch.
Okay, so level 1 is the hardware root. The initial immutable bootloader is stored in read-only memory, ROM, or a locked flash sector protected by the chip's hardware. Its integrity is verified by the silicon itself upon reset. This must be unchangeable. Then, level 2 is the application signature. The trusted bootloader takes control. It uses a public key hash, which is stored securely in OTP memory within the HSM, to verify the application firmware's digital signature, probably using something like ECDSA 256. The entire application binary has to be signed cryptographically by the team's private key.
If a competitor, despite RDP Level 2, somehow manages to install a piece of malicious firmware via some obscure side channel, what happens at Level 2?
The digital signature verification fails immediately because the injected code doesn't match the required hash. The VCU must refuse to execute the malicious application and immediately enter a safe recovery mode, usually preventing the high-voltage system from even enabling. This is the VCU's primary defense against persistent offline tampering.
That covers startup integrity. But what about when the car is running? How do we detect a sophisticated attack in real time, like an attacker who successfully cracked a key or bypassed the initial checks?
That's REQ-VCU 002, Runtime Intrusion Detection, or IDS. Since we can't use heavy network security tools, the VCU software implements a lightweight host-based IDS. It monitors parameters that are physically constrained.
Give me a concrete example of an anomaly that would trigger this IDS.
The most common attack vector we have to anticipate is a denial of service attack, a DOS, which often precedes or accompanies a replay attack. So the VCU monitors the cycle frequency of critical CAN IDs. If the nominal torque command frequency is, say, 10 milliseconds, but the IDS detects an external source suddenly spamming the bus, forcing the frequency to 1 millisecond, this is immediately flagged as a high-confidence DOS attack signature.
And the response has to be physical and immediate.
Absolutely. The mandated response is the VCU must instantly and physically cut the inverter-enabled signal, physically stopping the motor, thereby enforcing that hard safety boundary we discussed earlier. It's the ultimate self-defense mechanism.
Moving to the BMS, we need equally layered protection for the battery. BMS security starts with the integrity of the data it receives from the sensors.
Yes. Attackers love sensor spoofing. If they can trick the BMS into thinking the battery is safe when it's overheating, they win. REQ BMS 001 mandates robust sensor plausibility checks.
How do you verify plausibility when the data itself is the only source of truth?
You introduce a secondary mathematical model that predicts reality. The BMS must use an independent analytical model, perhaps a sophisticated Kalman filter or a robust thermal model, to predict expected voltage and temperature trends based on historical data and the current being drawn from the battery.
So if the model predicts the cell temperature should only rise by 1 degree per second, but the sensor suddenly reports a 50-degree C jump in 10 milliseconds.
That is flagged immediately as failure or attack. An instantaneous jump that defies the laws of thermodynamics is impossible. The system must then trigger a conservative response, power reduction, Or, if the jump is severe, opening the accumulator isolation relays, the ARRs, to isolate the high-voltage pack. The BMS cannot blindly trust any data, even its own sensor inputs.
And we have to revisit the charging phase vulnerability.
REQ BMS-002 directly targets the thermal bomb attack. The BMS must require the charger, that external low-trust system, to send a specific cryptographically authenticated handshake sequence or password before it closes the charging relay. This simple digital challenge prevents any malicious or unauthorized charger from gaining access to the battery system logic and initiating unwanted current flow.
Finally, let's address telemetry and wireless communication zone 3, the least trusted boundary.
This is the team's window to the world, and so it's the easiest window for an attacker. RQTEL-001 mandates strong encryption, AES 128 or higher for all wireless links, whether it's Wi-Fi or LoRa. And critically, we have to ban easily exploitable key management techniques.
Such as hard-coded keys.
Exactly. For LoRaWAN, you have to use OTTA, over-the-air activation, for dynamic session key generation. We strictly ban hard-coded keys, known as ABP mode, which are vulnerable to simple extraction and replay. For Wi-Fi, the bare minimum is WPA3 Personal, or ideally WPA2 Enterprise, with rotating certificates for maximum security.
And how does the architecture handle the active interference threat, the jamming attack?
RQTEL-002 addresses anti-jamming and data integrity. If the system detects that the wireless signal strength, the RSSI, suddenly drops or packet loss spikes, the classic signature of a jammer, it doesn't just panic, it has to activate local buffering. All critical data is automatically written to a secure onboard SD card or flash memory. Once the connectivity is restored, the system automatically resends the buffered data.
So even if the real-time link is sabotaged, you don't lose the data.
The integrity and completeness of the crucial race data are maintained, yes.
And what about the high-risk scenario of parameter adjustments being sent wirelessly? Can a chief engineer change the regenerative braking map mid-race?
Absolutely not, and the security reflects that extreme caution. Any downlink command to adjust vehicle parameters wirelessly is high risk, so we mandate a secondary authorization mechanism. This means the command has to be protected not just by standard credentials, but potentially by requiring the chief engineer's physical hardware token signature, or a second unique time-based cryptographic key. And furthermore, this action is only allowed when the vehicle is absolutely stationary or confirmed to be in a low-speed safe state, certainly under 5 kilometers, or adhering to strict FS safety rules that prohibit system changes during dynamic events.
We've established the defensive requirements. Now, the final step in world-class engineering, proving it works. Cybersecurity can't be a feature bolted on at the end. It has to be integrated into the V-model development lifecycle.
The integration is the key strategic differentiator. You have to use the TARA report to feed requirements directly into the design phase. We need to co-engineer solutions. For instance, the safety engineers identifying the unintended torque hazard in the HERA must work hand-in-hand with the security engineers identifying the CAN injection threat in the TARA. The resulting design, that truncated air with a monotonic counter, satisfies both safety and security requirements at the same time, maximizing resource efficiency.
And what about implementation best practices at the coding level? Simple coding errors often introduce the biggest security vulnerabilities.
We mandate adherence to stringent defensive coding standards like MISRA C.2012 or CERT-C. This is crucial for eliminating common low-level vulnerabilities like buffer overflows, which are lethal in embedded systems. And furthermore, integrating static analysis tools like CPCheck or Covariary into the continuous integration pipeline ensures automated vulnerability scanning happens with every single code change. You can't wait for the physical car to find a software bug.
Let's talk testing. The SOR specifies fuzzing. This sounds like throwing things at the car until it breaks. What is the engineering purpose of fuzzing for the VCU and BMS?
Fuzzing is deliberate stress testing against invalid input. You build a realistic hardware-in-the-loop, a HAL-PEST rig, a full-scale simulator of the car's environment. You then use automated tools, open-source CAN fuzzers like Carrying Caribou or commercial tools like Defensix to send massive amounts of random, malformed, or boundary-value data packets to the VCU BMS CAN interfaces.
So you are simulating a completely chaotic, aggressive attacker just flooding the bus with garbage data.
Exactly, and the passing criterion is absolute. The system must not crash, reboot, or enter an undefined state during the fuzzing storm. If anomalies occur, the watchdog timer must trigger a predefined, latching safe state reset. This is the best way to find those zero-day vulnerabilities in the input validation logic that developers might overlook.
Fuzzing tests robustness against chaos, but what about testing against smart, targeted attacks like the replay attack?
That requires penetration testing, REQ-TST-002. After the car is fully assembled, we mandate a black box test by an independent red team, ideally people who are not involved in the design or an external party. They simulate what a malicious competitor would actually do.
What are the key scenarios for that red team to execute?
They attempt real-world attacks based on the TARA, attempting to crack the telemetry Wi-Fi password, physically attempting to reset the VCU via the OBD port, trying to perform firmware extraction, and critically, attempting to record and replay the RES signal on the HL rig or a test vehicle. Proving that the RES dual-channel verification works under simulated hostile conditions is vital validation.
And you document every failure and iterate the design.
You have to.
Since failure is inevitable in extreme circumstances, that's the nature of competitive engineering, every world-class team needs an incident response plan, or IRP. How is the SOP structured to manage a security incident dynamically?
REQ-OPS-001 defines a multi-level incident response plan, integrating digital incident detection directly with physical safety response, which is crucial for the safety marshals.
Let's define those 3 levels of response.
Okay, so level 1 is an alert. This is for detection of minor anomalies, a high CAN error rate, detection of unexpected CAN IDs, or minor voltage jumps that don't violate plausibility limits yet. The action is to log the signature, send a real-time alert to the ground station engineer for human monitoring, but the car continues racing.
Makes sense.
Level 2 is limp mode. This is for detection of a sustained validated attack, like repeated FSAE authentication failures or continuous DOS detection. The action here is the VCU initiates a critical safety mechanism. It immediately limits motor torque to a safe maximum of 20% and vehicle speed to below 30 kilometers, guiding the driver back to the paddock under restricted failsafe power.
And the nuclear option.
Level 3 is total shutdown. This is for detection of catastrophic control loss, like illegal torque tampering that breaches safety limits, or confirmation of a complete control hijack where the VCU can't trust any of its core inputs. The action is to trigger the highest emergency process, immediately opening the high-voltage contactors, the ARs, and initiating the active discharge circuitry to ensure the bus voltage drops below 60 volts within the required 2 seconds.
And finally, after any incident, whether it's a crash or a confirmed attack, the team needs accountability and learning.
That requires the safety black box. We mandate that logs must capture all critical security events, every SecOC authentication failure, every unauthorized access attempt, every abnormal bus load fluctuation. And these logs have to be stored in protected, non-erasable memory, typically an OTP or an HSM-protected area. This preserved data is essential for post-race root cause analysis, allowing the team to continuously harden their defenses for the next event.
That is an incredibly comprehensive set of requirements, covering everything from global data compliance to truncated cryptographic hashes. For a newly formed university team, implementing all of this at once sounds impossible without infinite funding. As a strategic consultant, what is the recommended prioritized phased approach?
You are absolutely correct. Resource constraints dictate prioritization. The SOR outlines a 3-year implementation roadmap, applying that MEC analysis to prioritize foundational security over advanced hardening.
Let's look at the first year. Year 1, survival. What is the bare minimum foundation?
Year 1, survival. The focus is on foundational compliance and mitigating the easiest, highest impact physical attacks. Key milestones are physical network isolation, implementing that secure gateway between zones enabling MCU read protection RDP on all critical microcontrollers to protect firmware, basic WPA2 AES encryption for telemetry, and crucially, implementing the RES dual verification logic. Get the hard safety checks right first before you attempt complex cryptography.
Okay, year 2 steps up the digital game. Data integrity.
Year 2, data integrity. This is where you introduce actual security primitives that manage trust. Milestones include implementing CAN rolling counters for anti-replay and basic checksums across the PT CAN, deploying VCU Secure Boot, the chain of trust, to ensure firmware integrity at startup, and completing the first full, formal power report. This shifts the team from reacting to rules to proactively managing defined risk.
And year 3 and beyond, world-class, the final phase of maturity.
Year 3 plus. World-class. This is full system maturity, maximizing the competitive advantage. The team must implement the full hardware potential, deploying the HSM-SHE and the VCU and BMS master units, full deployment of the Leia lightweight CAN authentication protocol across the entire PT CAN, and installing the comprehensive vehicle IDS for real-time runtime monitoring. By year 3, security is entirely integrated and invisible.
So bring it all back to the starting point. What is the final strategic intent here? How does this massive technical complexity translate into winning races and designing the best car?
The final strategic intent is that security by design is the ultimate competitive advantage. A car that is digitally resilient and hack-proof is fundamentally a more reliable and stable car. If the VCU and BMS are constantly verifying integrity and authenticity with high certainty, the control strategies, the software that's driving the performance, can be pushed further, knowing that unexpected failures due to digital interference or attack are mitigated. This digital stability allows the driver and the control loop to run closer to the absolute physical limits of performance. In modern motorsport, security is not just protection, it is a direct driver of speed.
That's a powerful conclusion. Stability defines the limit of performance. For the engineering team that has just received this detailed blueprint, what are the three most crucial initial actions they must take tomorrow?
1. Organizational structure. Appoint a dedicated cybersecurity officer immediately. Security must have ownership within the team structure. 2. Hardware selection. Immediately review the VCU and BMS microcontroller unit selection. They must confirm RDP and HSMSHE support. If the chosen hardware doesn't support these foundational requirements, the entire roadmap fails before a single line of code is written.
And third,
3. Compliance audit. Complete the first compliance checklist against the specific requirements in FSG 2025 and FSAE 2025 rules to identify immediate gaps that must be solved before the next design review. The true measure of a world-class electric race car isn't just how fast it can go on the straight, but how reliably it can sustain peak performance when facing complex electromagnetic environments and potential digital threats. Cybersecurity is not just a protective barrier, it defines the limit of system stability.
what a fantastic deep dive into turning seemingly complex compliance documents and high-level strategy into a clear, tactical, and competitive engineering blueprint. This deep dive showed us how professional thinking can turn a daunting technical field into a clear strategic roadmap. We looked at Formula Student powertrains, but we have to ask you, the listener, what complex technical field in your industry needs this kind of strategic deep dive next? Let us know what blueprint you need unpacked. Thank you for joining us on the deep dive.